Katarina, you are on the stream.
Hi everybody, sorry for the confusion. I was not supposed to be the one talking. Welcome to this session called Intersecting Humans and AI. We have a very interesting lineup of papers today, and we are going to start immediately with the first paper by Fabian Sperle, which is also our Best Paper Award for this year's EuroVA. So without further wait, I think that we can roll the video.
Hi everybody, my name is Fabian Sperle, and today I would like to present our paper Learning and Teaching in Co-Adaptive Guidance for Mixed Initiative Visual Analytics. This is work that we developed in a collaboration between the University of Konstanz and the University of British Columbia. A few years ago, Davide Zeneda and his colleagues defined guidance as follows. Guidance is a computer-assisted process that aims to actively resolve a knowledge gap encountered by users during an interactive visual analytics session. Last year, they then explicitly specified that guidance follows a mixed initiative process. Marty Hurst has described such mixed initiative interaction as a flexible interaction strategy in which each agent, human or computer, contributes what it is best suited at the most appropriate time. However, what is considered best suited might change over time, together with the definition of the most appropriate time. Many other publications have argued that guidance should adapt over time, be sensitive to the current analysis context, and maybe even be personalized to the specific user. But, so far, there was no concise description of how and when these adaptations happen over time. In this position paper, we contribute a theoretical model of co-adaptive guidance that shows guidance as an interaction process. In this process, both the user and the system adapt in order to converge towards a common understanding of the task and the process to reach the analysis goals. The model highlights who initiates adaptation and characterizes the processes as learning and teaching. Before we get stuck in, let's have a look at a typical guided visual analytics process. Human and machine interact in a mixed initiative fashion, both contributing their strengths to make the process effective and efficient. In order to achieve this, both the user and the system rely on information that can be categorized in 3 models. These models drive the guidance process. While all of them can already contain information at the beginning of the analysis, their content is adapted throughout the analysis session. This adaptation then leads to an adaptation of the provided guidance. Let's look at the 3 models in more detail. First, the data model. The data model contains information such as data distributions, descriptive statistics, identified outliers, and relations and similarities between data points. As the user and the system maintain independent data models, the contained information can differ. The content will differ, especially with respect to the data points considered interesting, and might even reveal differences in the perceived similarities between data points. The task model contains all knowledge that is necessary to solve the tasks along the analysis process. An order to execute tasks in, the hypothesized solutions and relations and similarities between tasks. Importantly, the task model also allows capturing the analysis context in order to adjust the guidance accordingly. In addition to these 2 models, the user maintains a model of the system. This model contains objective knowledge, such as the implemented algorithms or available views, but also subjective knowledge that is influenced by previous experience in using this or similar systems. For example, in a user study that we recently ran, A participant was very confident in the abilities of the system. He said that he was expecting the functionality that we offered to just be there and just work because it was the year 2020. The system model captures these expectations and updates them over time, depending on whether the system is able to fulfill the expectations or not. On the other side, adaptive guidance systems should maintain a user model, where the system aims to model what knowledge the user has about the matter at hand, what their level of expertise is, what biases and preferences they might have, and potentially even the personality traits that each user possesses. As they stand, the models can be used to inform contextualized or even personalized guidance. But it is still unclear how this guidance changes over time. We suggest to look at guidance processes from the perspective of learning and teaching, and in order to do that, let's consider a guided mixed initiative visual analytics process between a user and a system. As we discussed before, both of them maintain their data, task, and system or user models, respectively. They interact via a user interface, and both keep track of the process. The user draws from their knowledge to drive the analysis process. In this example, the user begins to interact with the system. Based on a hypothesis and some initial data, task, and system model, they perform actions that can consist of one or multiple events in the interface. For example, consider a user interacting with a spatialization and adjusting the data points to reflect their mental model of similarity. They might relabel a few data points and move some to different positions in a projection view. In terms of guidance, we aggregate those actions into intents that characterize an intended change in the actor's data, task, and user models. In the previous example, the user's intent was to adapt the system's data model and teach it the user's perception of similarity between the data points. From the intent, users also derive an expectation of how the system will react. We'll come back to this expectation later. The actions that users perform are observed by the system and compared to an expectation that is derived from the data, task, and user model. Systems can then adapt their models depending on the user interaction. In our previous example, they could, for example, learn that all stars should belong to a single cluster and be separated from the crosses. As the user has performed the interaction with the intent of adapting the system's models, we call this guidance dynamic system teaching. The user is teaching the systems their view of the data. This dynamic is already often employed in visual analytic systems, for example when using semantic interactions. As a response, the system's intent could be to teach the user about some outlier data points that they might have missed in their previous interaction. Users compare this observation to their expectation and interpret the differences. The result of this interpretation can be both an adaptation of the user's models or even new findings that bring them closer to reaching their analysis goals. As the guidance was initiated by the system with the intent of adapting the user's models, we call it user teaching. Beyond those two, the co-adaptive guidance process also models system learning and user learning, where either agent initiates guidance with the goal of gathering information to adapt its own models. The whole model is described in more detail in the paper. For now, we focus on the 4 guidance dynamics that are important in co-adaptive guidance: user teaching, system learning, user learning, and system teaching. The 4 dynamics differ in how they are initiated and which adaptation they target. In this figure, user teaching and system learning are shown with blue arrows as they are initiated by the system. The arrows for system teaching and user learning are green, as these dynamics are initiated by the user. We argued that the success of guidance can, amongst others, be measured by the adaptation that it causes in its target. Consequently, the target is part of each guidance dynamic's name. Note that this is conflicting with previous definitions of user and system guidance, which, in our opinion, were ambiguous. It should also be noted that while the guidance dynamics serve to structure how we reason about guidance, multiple dynamics can be at play in a single system simultaneously. In the paper, we showcase some existing guidance approaches that prominently feature at least one of the 4 guidance dynamics. In the remainder of this presentation, I'd like to introduce the 4 dynamics in some more detail. First, system teaching. This is the guidance dynamic that we already demonstrated in the little example earlier. Here, users aim to teach the system their understanding of data, task, and analysis goals. System teaching is related to machine teaching, but can also convey information on personal preferences. Second, user teaching. This is the most common form of guidance in visual analytics, where systems aim to teach users something. In current systems, the provided guidance often focuses on overlooked regions of the data space or parameter settings that should be explored. Third, system learning. In system learning, systems request guiding information from the user in order to adapt their model. The most prominent example is active learning, in which systems assume control over the analysis process and users typically provide labeling information. Fourth, user learning. While many visual analytics applications offer views for data exploration and hypothesis verification, user learning appears to be the least prominent form of active guidance in visual analytics. In user learning guidance, users request information from the system primarily with the goal of adapting their models and extracting knowledge, and not necessarily advancing the analysis. In combination, all 4 guidance dynamics offer a powerful toolset for effective and efficient co-adaptive guidance. Future research should focus on identifying the correct guidance dynamics to provide. For more novice users, user teaching guidance could speed up the analysis process, while expert users can personalize the obtained results more easily when given the chance to perform system teaching. Developers should consider these trade-offs when designing systems and select appropriate guidance dynamics. With different user types and different guidance dynamics, all actors need to ensure an appropriate degree of adaptation. To support the users, this means, for example, showing potential uncertainty in the provided guidance. On the systems side, future research should investigate if and how teaching guidance by users should be rejected in certain circumstances, for example, when contradictory to previous interactions. Last but not least, enabling users to explicitly communicate their intent in terms of learning or teaching can let users make appropriate changes and provide more meaningful guidance. I have presented co-adaptive guidance for visual analytics, a view on guidance in which system and user co-adapt and converge towards a common analysis goal. Both the user and the system can assume control over this process, and they both aim to learn from each other while teaching each other at the same time. Consequently, system designers need to consider which of the guidance dynamics are most appropriate for a given system. Thanks for your attention. If you have any questions, don't hesitate to ask now or contact me after the session. Thank you.
Okay, thank you, Fabian, for the very interesting talk. And sort of, yeah, there are sort of some applauses on the YouTube channel, so some claps coming your way. So the first question we've got from the audience is from Venkai, who asks, how do you see your model work with different knowledge gaps and guidance degrees?
I think depending on the knowledge gap and on the guidance degree that is appropriate for a user type, we might have to pick different guidance dynamics, especially like I already said in the video. With novice users, it might be more appropriate to, for example, use more teaching guidance and try to give the system more control over the process so that it can lead the user through the analysis, whereas more expert users are likely to be able to externalize their knowledge more freely if they are given the chance of performing teaching guidance.
Thank you. One question I had, I was thinking, I think it's quite a broad set of dynamics that you introduce on these four corners of your model. I think which brings also a lot of room for new sort of experiments, new studies that needs to be done to understand how all of these dynamics run. So you mentioned that you've done some studies like about the expectations, and then when there's like mismatch between the expectations and what the system do. From your experience, what are some best ways of studying these dynamics? So what type of methods should we look for?
We haven't yet run a study where we explicitly try to compare different dynamics. The finding that I reported was from a different study where we told people that systems would learn from their interactions, and they were like, yeah, obviously they do. Why wouldn't they? Every system does that nowadays. But what we plan on doing in the future is implementing a system that can adapt between the different guidance dynamics and switch between learning and teaching. And then what I think would be interesting to measure in terms of metrics are, for example, the deviation that you have from a gold standard, whether teaching guidance might actually have the risk of misguiding you and teaching you wrong information, and then obviously user satisfaction and how much they perceive intrusion from the guidance of the system and distracting them from their task.
Yeah, and maybe an interesting question from Sylvia, which might relate to somehow like understanding these dynamics. Sylvia's question is, how do you detect the knowledge gap?
Yeah, very good question again. On the one hand, we could do kind of entry interviews when users start to use the system. We could give them a few questions, kind of assess how good their performance is in order to pick a general dynamic, and then to identify the knowledge gap later on. I think there's a vast host of different techniques that are being used out there. Last year at Viz and some of the workshops, there were techniques that used eye gaze detection, and we had the paper on stress detection from Chris Collins and his student. So I think in our model, we didn't particularly focus on identifying what the exact knowledge gap is, because there are lots of different techniques out there, logging interactions, logging eye gaze patterns, logging heart rate, and so on, to identify when users might need help.
Yeah, those are really interesting. I think all of these are very interesting research directions. And I guess one remaining challenge is how to balance and how to switch from these different strategies and different roles, right?
Exactly. The goal should be to actually enable this mixed initiative process that we always have in mind when you think about visual analytics, where both the system and the user are both contributing their strengths and their information that they have about the domain and about the data. So that's definitely the remaining challenge.
Thank you very much, Fabian, for your responses as well, and congratulations again for getting the best paper award.
Thank you.
Lots of claps from the YouTube channel as well. Okay, so next in this session we have Gabriel, is in Brazil, joining us. He's going to sort of the talk will be on a generic model for projection alignment applied to neural network visualization. And we hear Gabriel's talk first, and feel free to type your questions on the YouTube channel and on the Discord discussion.
Hello everyone, my name is Gabriel Cantareira, and I will be presenting our work at the EuroVA 2020, titled A Generic Model for Projection Alignment Applied to Neural Network Visualization. Let's start with a quick introduction. Multidimensional projections are techniques that transform high-dimensional data into low-dimensional data while preserving relationships between data points. This usually means points that are similar in their initial space will remain similar in reduced space, and points that are dissimilar will remain dissimilar, which is useful for visualization. A particular application of these techniques is in XAI, where it is used to explain how machine learning models perceive data. Here, we have some examples of multidimensional projections in neural network visualization. These images show activation outputs from hidden layers, highlighting how groups are formed or which instances are misplaced. Some of these works also aim to explain the evolution of representations in the network, comparing projections from different layers or training epochs. In those cases, we have a problem. Most modern techniques, like TSNE or UMAP, are nonlinear. This means that there is not a direct relation between projection results and original data. If you want to compare projections from the same dataset at different time steps or processed through different means, there are no guarantees that a difference in the projections will translate to a difference in the data. The fact that 2 points became far apart in 2 projections may not mean that they became more different in the 2 versions of the data you are projecting. The images below are TSNE projections with the same initialization parameters of outputs from the last hidden layer of an MLP with slightly different weights, with the same data instances as inputs and without expressive change in accuracy results. For instance, the red group moving around does not likely represent a change in the way the system perceives data, but rather a consequence of how TSNE builds the 2D space. So, we want to achieve aligned projections. We are considering different feature sets from the same data. For example, we may try different pre-processing methods and want to see differences between the results, or we may have a processing pipeline with multiple steps and want to see what each of them is doing to our data. Irrelevant variability must be removed, meaning that, as much as possible, differences between projections must lead to differences in feature sets. Also, there's a bunch of different projection techniques and we want to be able to use them all in this context, so a general model would be nice. What does this mean for neural networks? Well, we want to be able to compare projections from multiple hidden layer activations of the same network, or activations from different networks to see their differences, or maybe see how training is making our models separate data along multiple epochs. Here on the right, we show 2 examples of how projection alignment fits into workflow. We can project data from multiple steps of the same process, or project results from multiple processes and compare them. There are techniques that already do this to some extent, namely dynamic TSNE and visual feature fusion. But if you try to simply cut the alignment part of the algorithms and put it inside other projection algorithms, or use them in different applications, you run into some problems. First, they are more restricted to their specific applications. The TSNE aligns projections in a sequential fashion. This is not good for cases in which feature sets are not sequential in nature, such as the comparison between different models. Projections that are far apart in the sequence, such as the first and last, may not be properly aligned. VFF is focused on global distance preservation, calculating a single projection beforehand to use as guide for the whole process. Feature sets also need to be normalized as to be consistent regarding distances, since the number of attributes in each feature set may differ. And finally, since each projection technique uses a difference optimization, if you simply plug an additional term into other technique, the numbers won't match. We need appropriate parameterization to make them comparable. This is how we propose to achieve these goals. We add an alignment cost term to any gradient descent-based projection technique. This term indicates how different each projection is to all the others, and will be minimized as part of the optimization. We need to perform normalization for different feature sets. This is relatively simple, but important to mention, since the most common approach is to normalize attributes within each feature set, and we need to normalize pairwise distances instead. All techniques mentioned in previous slides use the lambda parameter to control the influence of alignment in the process. However, when adapting cost terms to other methods, lambda completely loses meaning. For instance, the default value for lambda in the original DTSNE paper is 0.1, but I tried transferring the same cost function term to UMAP and had to try out values around 0.001 or 0.005 to avoid having all projections turn out identical. VFF works well with lambda values around 0.3, so you can't really tell what a lambda value will mean for different techniques. This is the normalization we employ in our approach. We divide all attributes from each instance in a feature set by the mean norm of instances in that feature set. This can also be done after regular attribute normalization is applied. In this way, we ensure that the mean norm for all feature sets is always 1, and therefore we can compare distances between them. We could also divide by the maximum norm, so that all norms fall between 0 and 1, but since we do not know how feature sets will be produced, we want to avoid outliers. And this is the equation for our generic model. Ct is the new cost function for the whole optimization. C, projection T, is the regular cost function for the projection technique that we are adapting. And C, alignment T, is our plugin term for alignment. The cost T alignment T is given by the sum of distances T, in this case, Euclidean distances, between each point in the current projection Pt and the mean position of the same point in all projections, given by P over line. To put it simply, if the position of any given point in a particular projection is too different from the position of the same point in other projections, the resulting cost will be higher. The lambda parameter defines how much will alignment influence in the result, between 0 and 1. Alignment cost is multiplied by lambda, while projection cost is multiplied by 1 minus lambda. Gamma is a positive scaling parameter, which we will discuss in more detail in the next slide. I talked about it before, but what does scaling really mean here? The problem is that cost functions behave differently according to each projection technique, not only by moving quicker or slower towards a minimum, but also with different second-order derivatives, meaning faster or slower acceleration. For instance, let's look at learning rate parameters for TSNE and UMAP in common Python implementations. Despite achieving stop criteria in a similar number of iterations, there's a 20,000% difference in learning rates. Another way of observing this is to simply plot the cost values or gradient norms over iterations for the two techniques. The gradients obtained at each step for each method are highly different in magnitude, and adding the same alignment cost term to the two equations will lead to unbalanced results. This will occur when using the alignment cost from other techniques as well, not just this one. The lambda parameter mentioned before can compensate for this. However, we want lambda to control trade-off between alignment and projection, and do not want to overload it with scaling. Therefore, we include gamma. The alignment cost function has its own behavior, and so scaling also interferes with when alignment optimization will kick in. For instance, higher gamma values will result in higher costs, and therefore alignment will be more likely to be prioritized when optimization starts. Our goal is to make everything as consistent and comparable as possible, so we took a different approach. We automatically define a different gamma at each iteration. When generating the final gradients, gamma is equal to the norm of the projection gradient divided by the norm of the alignment gradient. This means the pull towards alignment and distance preservation will always have the same strength, and their influence controlled by lambda. So, we now have a single parameter and its final effect is more intuitive. When it comes to our results, we applied our method to enable alignment in UMAP. UMAP is a projection technique that is quickly becoming popular for visualization, and we thought it would be useful as an example. Our experiments were conducted using neural network data from existing models in literature as well as ones of our own design. Our goal with these experiments was to align projections from data with varying amounts of features to observe if alignment would still hold reasonably. To align projections from different models and observe if we could identify differences in their behavior. And experiments pertaining to UMAP properties to determine if our approach would hinder UMAP's advantages in any way. The presented experiments were conducted using our proposed method for obtaining gamma and lambda equal to 0.1. We performed other experiments, such as adapting TSNE with our method, using different parameters, or projecting data from different domains, but they were not included in the interest of paper space and presentation time. This is our first experiment. We used a convolutional network with 2 convolutional layers and 2 dense layers, trained on the MNIST dataset. This was done mainly to observe how the network would create abstract representations, ones that could easily be correlated with visual cues from the images, and how layer outputs with different dimensions would be represented in projections. These images show 2,000 test samples from the dataset projected as output of each of the 4 layers. Instances are images of a written number equal to its class, shown on the right side. With each layer, separation between classes becomes clearer, and classes that are visually similar, such as the numbers 4, 7, and 9 in the top region of the projections, start mixed up and become well separated, even those too close to each other. In this experiment, we show projections from the last hidden layer of 2 different models. This experiment uses the CIFAR-10 dataset, and the models are the same convolutional model from the previous experiment and the VGG16 network. The accuracy results for both these networks on test data is similar, so we try to observe if there were any differences in the way data is perceived. We project the less hidden layer activation data from 2,000 test samples. While the tested models achieve similar accuracy results, VGG16 has concentrated groups that are absent in our CNN model projection. These groups indicate a higher amount of certainty in their classification, but may also be a sign of overfitting. A whole grid of model comparisons can be built in this manner, while the representations generated by each network can be observed side by side and provide insight on model behavior. Finally, this experiment compares less layer activations from an MLP model and the CNN model defined before, using MNIST data. Both models achieve high accuracy results, but the MLP model has more trouble separating a few instances. This is where we aim to observe if UMAP's subtle advantages are kept with our alignment method. As in previous experiments, activations from 2000 samples were projected. Our UMAP adaptation, shown in the top row, is able to show how MLP keeps certain classes close together in a more noticeable manner than the TSNE, mainly due to how it better preserves intergroup distances. This is highlighted in regions A and B. Additionally, our adaptation does not make expressive impact on the original UMAP's algorithm performance. And this concludes this presentation. I would like to thank the chair and all viewers for their time. My contact information is displayed for any questions or research ideas. Thank you.
Okay, thanks, Gabriel, for the really interesting talk and a very interesting technique. It's a challenging problem to sort of to make these alignments. I'm looking at just one last time if I'm missing any questions. Don't see any yet, but so I'll start with one, and maybe one that's sort of a bit general. So because comparing multiple projections is a problem that you can have not only in the context of like neural network analysis, but outside this, and there have been some work that has been done on that. So how different is this context, do you think? So what are some specific challenges that you came across within this projection alignment for neural network analysis?
Well, mainly the data, if you're trying to see this in a general manner, you're just trying to compare different, it's separated the number of things you're doing with data at each comparison. For instance, if you're trying to do some sort of pre-processing and you want to see how each of them changes the data, you're just comparing these pre-processing techniques. If you're trying to go to see data that goes through a neural network, you are also having to compare data that has a different number of attributes that may be widely different in not only scale, but the values themselves and the distribution of values may be highly different because of the operations that each of the layers do into all of the data instances. So I think the biggest issue we have when dealing with neural networks is that there's many different transformations going on in the data at the same time, whether if you're trying to compare different layers from the same network or a given layer of different networks.
Okay, great, thank you. I have a question from Andreas Interreiter. And he says, one approach to get a common embedding space is to project all the data together at once. And have you compared your technique to this approach?
Yes, the main problem with projecting all the data at once is that you may, in some cases, it may be too much in terms of performance because when you project all data at once, you have to compare pairwise distances between every single data instance. So if you're trying to do, say, you have 2,000 points in 5 different states, instead of having to compare 5 projections of 2,000 by 2,000 distance, you now have to compare a large projection of 10,000 by 10,000, which may lead to some problems in terms of performance. And the other issue is that if you try to do a single projection with, in case of neural network layers that have different dimensions, it will not work so well because you'll have to find a way to equate this data into the same projection, even though they have a different number of dimensions.
Okay, great.
I mean, sorry, just to make an additional point, is like the attributes may not mean the same thing for the different projections, for the different feature sets that you're analyzing. So it wouldn't be as reliable to just project them all at once.
Great, thanks, Gabriel. Another interesting question on the YouTube channel from Marta Ferreira. She's asking, is it possible to use this projection in an iterative way to modify the network and maybe obtain better separation between classes? And I think that's a very interesting question that relates to some of the things that we discussed today, like progressive analysis and you having progressive methods and iterative guidance methods, and which also probably relates to Fabian's talk just we heard.
I feel like the results that we're getting so far point towards this direction, but we don't have concrete experiments done on that area yet. But I feel like interaction with these projections could be done in order to achieve, like, if you get a different separation in one network when you're comparing to the other, and you're thinking, how am I going to transfer the properties from this network to the other one? And you can see the areas and the points that need to be better separated. And these could be, since we're dealing with direct activations from a determined layer, you can alter layer parameters in order to achieve that separation that you wanted from seeing the other models.
Mm-hmm. Yeah, I think then that's like demonstrating the applicability of these projection alignments in the context of refining and debugging a machine learning model, right?
Yes.
Yeah. And then maybe just one final question that I had. Like when you showed this two different projections from two different techniques, and we saw that I think on the second one you have lots of overlaps between classes, which indicated not a good separation, right? So there was also a performance indicator. When you looked at the projections that your approach produced, have you compared it to actual quality, actual performance of these systems?
Yeah.
And then the visual quality. I mean, is there? How are they aligned?
Sorry, in this case, we're talking about the last projections or the second to last one. With the different networks are the same two networks in two different techniques.
Yeah,
this one,
yeah, that one.
Yeah, because this was we did this experiment to actually see if some of the UMAP's properties would still be retained in this context, because the UMAP is known. UMAP is known to better preserve global distances when compared to TSNE. So the intercluster difference should be better. Should be more similar to what we would expect in the real data. So if these groups are closer together in one model than in the other, it means that this model is having, I wouldn't say more trouble, but this model sees them as more similar. And some other techniques may miss this feature due to prioritizing different aspects of visualization and projections. So what we try to see is which class, in that case, which classes are still being seen as similar, or there is like a mixed region between these two classes, and points that can be seen in the threshold that could be tweaked between one class and the other with really small changes in the parameters and weights in the network.
Right. Thank you very much, Gabriel, for your talk and also for responding to all the questions in great detail. Thank you.
Thank you.
Yes. And next up we have Tatiana von Landesberger, who is going to present the next paper. And this one is particularly quite interesting for all of us who are now sitting at our homes or offices due to a pandemic. And this one is how visual analytics can be used in controlling a hospital infection control system. So the paper is called Visual Analysis for Hospital Infection Control using an RNN model. It has many quotas, so it will take me a very long time to go through all the names. So it is always a very good indicator of a very strong collaboration. mix of medical doctors and visualization researchers, which is impressive. So I'll leave the floor to Tatiana's talk, and as before, feel free to post questions during the talk, and then we'll continue with the Q&A after the talk.
Dear Session Chair, thank you very much for the introduction. Dear audience, it's my pleasure to present our work on visual analysis for hospital infection control using RNN models. It is a result of a cooperation between computer scientists from Technische Universität Darmstadt and Karlsruhe Institute of Technology, together with infection control experts from university hospitals in Heidelberg, Göttingen and Hannover. This work has been done in a common project called HIMED over a 2-year period. The motivation for our work comes from the need to early detect and prevent pathogen outbreaks in hospitals. Bacterial and viral infections endanger patients in hospitals worldwide. Among these, so-called anti-drug-resistant pathogens, such as vancomycin-resistant enterococci, are difficult to treat and require the use of last resort antibiotics. Pathogens are transmitted among hospital patients by direct contacts or via contaminated places in the same room or at the same ward. These infections obtained in hospitals are a threat to patients' health, and they also increase treatment costs. As many infected patients do not have illness symptoms, dozens of patients might get infected before the infection is detected. Infection control experts such as hygienists, clinicians and hygiene experts need to develop strategies for early detection of pathogens in hospitals. They need to detect outbreaks and identify potentially infected patients. They need to detect when and how pathogens could be transmitted. It means to identify factors that support pathogen transmission. This helps them to determine preventive measures such as disinfection of rooms and patient isolation. Currently, the infection control experts perform these tasks mostly manually, using long lists of infected patients. This is time-consuming and likely error-prone. Currently, visual analytics approaches focus on disease spreading in large populations. They show the number of infected persons over time and spatial distribution of infections. Recent approaches also focus on disease spreading in hospitals, and they focus on future disease spreading prediction. We present a novel approach that learns a recurrent neural network for detecting potential infections and factors that support pathogen transmission. Our novel interactive interface enables infection control experts to explore the model results with respect to their tasks. The recurrent neural network model enables us to classify each patient in each time moment as infected or non-infected. The temporal facet of modeling is important for determining when patients get likely infected. We use time-dependent features that are available for each patient on hourly basis. Based on clinical expertise, we use the following features: type of patient stay, such as change wards, hospitalization or surgery, patient location, wards and rooms, and number of infected patients in the same ward and in the same room. As training data, we used real detected patient infections. We used the mentioned features and weighting for balancing between infected and non-infected classes. The training was performed before the visualization in an offline mode due to the long training duration of several hours. We present a novel interactive visual interface for exploring model results specifically for the needs of infection control experts. Our interface has 5 linked views: confusion matrix for the whole hospital, confusion matrix per ward, epidemic curve view, infection transmission timeline, and a feature view. I will now explain each view. The confusion matrix shows the results of the model, true positive and false negative results, as well as false positive and true negatives. We distinguish between false positives that are true errors and false positives of those patients that were not screened. These patients are potentially infected and could spread the disease further. The colors from the confusion matrix are also used in other views. For example, we can look at the confusion matrix by word. As words are organized hierarchically, we can see that the word number 70 has a very high number of positive infections and also of potentially infected persons. Our extended epidemic curve view shows not only the number of infected patients over time, but also the number of potentially infected patients. See the blue, red, and green lines. The infection control expert can focus on time periods with high number of potential infections. The patient timeline view shows when and how the model predicts infection transmission. The background color shows the patient's stay in the hospital and infection status. The horizontal bar shows at which ward the patient stayed in the hospital. The vertical lines show the infection transmission predictions by the model. We see the dark color shows that this infection is highly probable because the patient had contact to 18 other patients. The feature view shows the attention features for the wall model, black bars, and for the user-selected transmission event. Red bars mean lower feature weights and the blue bars mean higher feature weights. In cooperation with infection control experts, we apply our approach to real-world data on infections by vancomycin-resistant enterococci in a large German hospital. This pathogen is relevant for hospital infections worldwide. In this use case, the infection control expert wants to detect the potentially infected patients and the causes of VRE transmission in order to derive strategies for better disease control in the future. We used more than 88,000 patient cases over 3 years. RNN training was done on 80% of the data and testing on 20% of the data. We evaluated standard performance measured, and together with the confusion matrix, the results show good model quality. We would like to note that our goal was not to create the best fitting model, but rather to investigate the usefulness of using and showing RNN model results for infection control purposes. The infection control expert wants to analyze the increase of high VRE infections in summer 2011. Therefore, the time filters were set to that period in the epidemic curve view. He looks at the confusion matrix to detect possible infections. The matrix for summer 2011 shows 54 already known cases and also 83 additional potentially infected patients, so the outbreak was possibly larger than already known. A look at the confusion matrix for wards discovered the ward 70 in the area 1026 with an elevated number of potential patients. This ward is a potential location of the outbreak. The transmission timeline view reveals that the model detected a high likelihood of the first transmission event. See the dark vertical bar with 18 persons already 2 weeks before the first positive screening was monitored. See the orange background. This indicates that the patient was earlier infected than known, and thus he could have infected other patients before being isolated. The expert is now interested in factors supporting the VRE transmission. Thus, he looks at the feature list. It shows a long blue bar next to the feature accumulative number of infected patients in the room. This means that this room is a potential cause of the infection transmission and thus needs to be disinfected. The effect of this intervention needs to be analyzed in a follow-up study. To summarize, we presented a new visual analytics approach to support infection control in hospitals. It learns a recurrent neural network model and shows its results in a new interactive visualization. We applied it to a pathogen called VRE. However, it can be applied to also other pathogens appearing in hospitals. The evaluation with infection control experts showed advantages of this approach. In the future, we wish to extend the model and the visual interface with additional information, such as input data uncertainty. Thank you very much for your attention.
Thank you very much for your presentation, Tatiana. Very interesting and current work, like Chagatai pointed out. There are applause coming up in the chat. If whoever wants to pose questions, you can do that on YouTube and on Discord, and we're monitoring them. And in the meantime, I can start. This is very interesting work, and as you said, it has been going on over quite a long period of time. Could you share some details on the design process that you have followed for the implementation?
Yeah, this is a very good question. I think it took us at least 1 year to understand what the doctors and infection control experts are talking about, at least to understand the data, because there are dozens of viruses and definitions. When is somebody infected and when is somebody really ill, and that there is a difference between being infected and being ill. So now when I followed the coronavirus discussions on TV, I was like, yeah, this is what we have been talking about. And also there are many stakeholders. There are infection control experts, the hygienists in the hospital. Then there are infection control managers, are kind of bosses that do the strategy. Then the data analysts that take data from the hospital systems. They need to use several hospital data systems and merge the data, because the data about the patient locations are in one system and the data about infection status is in another system, and the so-called microbiologic data that says that when people got, for example, were tested or were not tested are in a third system. So this data needs to be merged first. So it took us a very long time to really understand the structure of the data and the tasks they need to perform, because there are different goals. People have different goals. There are people who want to know how many infected patients are in my location or in the whole hospital. So, and another challenging part is that people move through the hospital. So it can be that you don't see many infections at one ward, but still you have an outbreak in the hospital, because in the meantime, the patients moved between the wards. So this is very, I think the understanding of the data and understanding of the task was the most difficult part of the process.
Just relating to that, how was the system perceived following this by the sort of experts? Has it been adopted successfully in a sense?
Yeah. We had several iterations of the system. One of them was presented as a poster last year. So this is like, I don't know, 50 iterations or something. And this is also one challenging thing, is like everything that is more difficult than a bar chart is not going to be accepted, more or less. So they have many of the views that are presented here in the system. They are based on views that they already use. For example, the timeline that we have for the one patient, they create per hand in Excel by really coloring the Excel cells. One would not believe that. So we try to reuse the designs that they already are familiar with. Like, for example, this timeline view, and also the confusion matrix. Many of them are researchers in a way that they doctors. These are university hospitals. So some of the hygienists and infection control experts, they do research on their own. So they were familiar with confusion matrices. So we use this type of visual design and augmented it with the results of the model. And I think this was the driving aspect, is not to present something completely new from the scratch, but try to reuse what they already know, so that there is less learning curve needed. We tried sometimes to present completely new things, but the acceptance for that is really low.
Yeah, I can imagine. We have several questions here from YouTube. Leandro Luque asks, is it possible to add more information to the RNN, or the three features are enough to make, or are the three features sort of enough to make predictions?
Yeah, we have kind of 50 features that we also reduced, because we don't want to do over learning or overfitting of the model. So we did dimension reduction of the features to 25 features in the end, and more or less we used all the features that are there, that are available from the system, because at the first we didn't know, and the infection control experts also didn't know what kind of features are likely to be supportive for the modeling. So we tried first to use all the features that are there. And in the end, we ended up with those 21 features that covered both a number of patients in the room, meaning that the more people are in the room, the more contacts the patients have to other people. So the more likely they are to get infected, in case some of the other patients that they have contact to are also infected. And also the knowledge from the expert told us that there are rooms and there are wards that have high frequency of people that come and go, and or they are more likely to get infected. So we also used which room or which treatment do the people get, because if you have a lot of treatments, also you are more likely to get infected, just by having contact with many people.
Another question here from Yukong Zhang is, he wonders, what triggers you to use an RNN, and have you considered to use other types of neural network?
We went directly for RNN because of the time dimension that it offers. It was important for us to know when people get likely infected, because then we can trace back with whom did they have contact after the pathogen transmission. However, for the future, we would like to use also other models and try out also other models and try to improve the modeling for the future. This is a first step that we started, and for the future, we would like to compare various models.
Thank you for that. Andreas Keren asks, medical doctors have usually no time, and how was their reaction on the VA tool? Sort of, you partly have answered this already in the discussion about how it was accepted, but how was them?
Yeah, having little time is true. We provided remote access to the system to some of the doctors that were interested. We had online sessions where we talked to them. We were very lucky. This is a common project, so they were very cooperative and are very cooperative, and I hope we stay in cooperation also in the future. So it was also their own interest in the project to get better tools for this, and in this case, I very much appreciate the cooperation.
One final question. MD that's presenting next wants to hear a little bit more about the confusion matrix. For example, you could expand the matrix, as you said. How does it help to understand the results?
Okay. The confusion matrix shows the results of the model. So how many false positives, true positives, false positives, false negatives, and true negatives do we have? And also helps to identify people who might be infected but were not detected by the test. It's important to know that not all people in the hospital are tested on everyday basis. We know it also from the corona, so that the number of tests is limited, or you can't simply test everybody every day. So the confusion matrix also shows people or the patients that are likely to be infected but were not detected by screening. And this can be counted by the model for the whole hospital, or per so-called house. Some hospitals, they have different areas, so you can have the confusion matrix for the whole hospital, for the area, per ward, or even per room. So we show basically the hierarchy behind it, that we see how many infected patients are there per whole hospital, or per area, or per ward.
Good. Thank you very much, Tatiana. The final question is, has it been used for tracing COVID in hospitals?
We are working on it, to be honest. We are working on it, and I hope we will get some results soon.
Yeah. Thank you very much for your presentation. We will now move on to the final paper of our session, and it's called Interactive Visualization of AI-Based Speech Recognition Text, and it's MD Amiruzaman that is presenting. I'm sorry already. His co-authors Tsung-Heng Wu is also here, and Yang Zhao. And go ahead. We'll play the video.
The title of our paper is Interactive Visualization of AI-Based Speech Recognition Text. Speech recognition techniques has achieved impressive success recently with AI techniques of deep learning networks. Speech-to-text tools are becoming prevalent in many social applications such as field surveys. However, the speech transcription results are far from perfection for direct use in these applications by domain scientists and practitioners, which prevents the users from fully leveraging the AI tools. In this paper, we show interactive visualization can play important roles in post-AI understanding, editing, and analysis of speech recognition results by presenting a specified task, characterization, and case examples. Speech recognition is an important field in computational linguistics. For many years, researchers have developed a variety of technologies and tools to identify the words and phrases in a spoken language. Cloud-based speech-to-text services have been provided by many big companies such as Microsoft, Google, using deep learning models. Also, users from multiple domains are eager to utilize these AI tools for real-world applications such as conducting field survey and collecting user opinion. There are three practical problems. Number one, a fully Full speech is recognized as a group of fragments, which usually do not present natural sentence or paragraphs from a speaker. Number 2, errors of audio recognition is inevitable, and quality varies greatly. Number 3, the confidence score of words and fragments given by the speech recognition algorithm sometimes do not reflect the real probability of misrecognition. Domain scientists face challenges to effectively complete mainly 3 tasks in collecting lengthy audios from multiple speakers. Number 1, understanding the characteristics of speeches as well as speaker. Number 2, manually editing the massive speech to text results. Number 3, analyzing and comparing multiple speeches and speakers. There are 2 major contributions of this paper. First, we identify the characteristics and shortcomings of AI-based speech-to-text results. Then, we propose major direction that visualization technique can promote their usability. Number 2, we develop a prototype to showcase the usefulness of visualization tools, which combines visual metaphor and semantic and sentimental analysis. To do the work, we have divided this whole task into 3 phases: test and fragment confidence, semantic and sentiment attributes, identification of visualization task and functions. Speech fragment, which based on speaker's narration style and talking speed. We computed the term confidence for each term and fragment confidence for speech fragment. Term frequency is to identify the top term in a speech. We computed term fragment and sentiment to capture speaker emotion, and term entropy to capture the diversity of attributes throughout the speech. During the requirements analysis, we finalized 3 tasks. Number 1, helping the user quickly understand the structure and characteristics of recognized text. Number 2, allowing users to discover and compare semantics of speeches and sentiments of speakers. Number 3, guiding the revision of transcript to achieve better quality for downstream applications. Speech-to-text AI tools are prevalent, while results are often need to be revised and investigated to discover errors and understand the speech or speaker's feature. A set of visualizations are presented in this type of emerging data. It is useful for many post-processing tasks in a variety of applications. As for the future work, we intend to incorporate more visual designs, effective and guided interactions, and evaluate the system by domain users and formal studies. Now I will show you a demo of this system.
Creativity. Those of us who've had the singular privilege to hold the office of the presidency know well that progress in this country can be hard and it can be slow. We want to open the gates to opportunity, President Johnson said. Because of the civil rights movement, because of the laws President Johnson signed, gates to opportunity, President Johnson said. Because of the civil rights movement, because of the laws President Johnson signed, we want to open the gates to opportunity, President Johnson said. Because of the civil rights movement, because of the laws President Johnson signed.
Okay. Okay. Are we?
I'm ready.
Good. Thank you very much. And now I'm hearing myself. So this. Thank you very much for your presentation, Emily. Please feel free to pose questions in the YouTube chat and Discord. In the meantime, I see already some questions coming up. So a question from Shivam Agarwal is, how do you quantify confidence and sentiment in the speech?
So Google and Microsoft has different types of API that you can use to compute those confidence and also sentiment. So what our work was to show basically that how visualization technique can help to understand and also analyze, a little bit dig into deeper in that sense. So the confidence and sentiment basically came back from APIs. Does that answer your question?
Okay. Mm-hmm. And has sort of the results of your that you show, have you sort of evaluated them?
Yeah, we have
a
small group of users to do a case study. But what we want to do is in our full work, we want to incorporate a little bit more of more user studies and go a little bit more deeper on that. So far what we have done is that the confidence and sentiment that is coming back from API, we wanted to show that they are really accurate or how good they are. So a user can actually identify those things, as you saw in our interface, that we presented all the confidence values, and you can filter them out, like different types of confidence interval, and you can see which one was identified as a high confidence, which one was identified as a low confidence, and then maybe you want to see why was that. So in AI deep learning models, as we all are familiar, that one of the thing happens, two things you can fix. One is that you might be able to fix the model, or you might be able to fix the data. So our approach was to show that before you go into the model, you might also want to see where my data is having trouble, like why that may be. You saw we had two speech example one from President Obama, actually three of them, one from President Obama, one from President Trump, and one from Martin Luther King. And where the API could not recognize, we wanted to show that why that was the case. So user can actually go into that detail and see how the API found the confidence and the sentiment, and then is it the true case or is it something problematic thing. So that was the idea.
So that, I mean, this type of error or discrepancy, that is done then interactively, sort of checked by the user.
Yes,
there is no...
Yes, exactly. And so far that I know of, this is the one kind of work, nothing has been done in this domain, in this regard. So there are a lot of rooms to improve. There are a lot of things to do. We just wanted to push this idea as quick as possible so that other people maybe want to work on that and maybe improve. So.
But that connects well to the question from Chagatai here, who asks, in what ways do you think that this can improve speech recognition systems?
So first of all, like I said, that the model might be one of the problems. So in deep learning, what we do, it's still a black box. We pass something and we get the result. Magically, we get the result. Now, like I said, that one of the things people are pushing into, as you can see from, I think, 2002 thus far, what people are doing is making the model more and more complicated, adding layers and layers and layers and layers. So if you want to have better result, of course, you want to add more layers. And as you add more layers, it does complicate the computation as well. So it will expand. But also another thing is that you might be also able to look at your data, the data set you are training or data set you are testing. Are there any issues that my results are not as accurate? So our approach, like I mentioned, that it's giving an insight of looking inside the data, like, okay, I got this with 85% accuracy, for example. Where did I lose my accuracy? Can I see that result? Like almost Tatiana's result was, she was allowing us to see the confusion matrix, to see, dig down where problems might have happened, false positive, false negative. So in our case, we also want to do the same thing in a different way, and also compare, like, okay, if one person was talking, is that the person who is speaking, that's the problem, or the word had some problem, or the recording had some problem. So that kind of thing we kind of wanted to show.
Okay. And is there, in relation to that, is there any way, do you have any sort of way of actually interacting with the underlying algorithms? Again, a question by
yeah, that's what we're trying to do. So our next approach would be to compare different algorithms and see if one algorithm is performing better than the other, and if so, where that might be the cause. So cause an issue, we are trying to like dig into deeper on that. So that's our next step.
Very nice. Okay. Thank you. Then I would like to thank you for your presentation and for answering the questions. And I would like to thank again all the speakers of this session and the nice discussions, even though they were by proxy, that have occurred during the afternoon. And with this final applause here, we would like to go in directly into the closing session of EuroVA this year, where we will more formally apply our thanks to everybody. And I think that it's good if Chagatai can share his screen, since he has the final PowerPoint that we will use.
Yeah.
So in the meantime, I would like to go ahead and say that it has been a really interesting day, and given the current situation, even though it is unfortunate that we did not get to meet all together live, I think that the day has progressed very well, and we have managed to have a really nice workshop this year also.
I think we have the slides up, Katerina, now.
Yeah. So let's have a quick recap of from the opening sessions.
Are you going forward?
Yes.
Okay, good. I'm changing the slides.
Okay. So just a quick recap, new for 2020 is that EuroVA from this year will be in Scopus, which which will increase visibility of all the EuroVA papers. And this will include both past and future publications, which is really good and nice advancement. Also very nice for this year is that all the papers are available open access. And the next thanks goes to the past year's co-chair, Tatjana von Landesberger, who has served as a EuroVA co-chair from 2018 and 2019. And Jörn Kohlhammer has wants us to notify you, Tatjana. Thank you greatly, and notify you that you will get this certificate in person when you meet him next time. We would like to congratulate the best paper for EuroVA this year. That is Learning and Teaching in Co-Adaptive Guidance for Mixed Initiative Visual Analytics, and is presented to Fabian Sperle, Astrid Geitler, Jürgen Bernard, Daniel Keim, and Menna El Asadi. And they had a really nice presentation, and it triggered very nice discussions. And we have seen several talks today that have been relating to suggestions and notions that have been raised in this paper. So congratulations and thank you very much. Of course, we would like to thank all of the speakers, all of the session chairs, and all of the audience for being active via YouTube and via Discord, for all the questions you have been posing, and making sure that this has been a sort of lively session, even though it has been virtual.
Can I jump in and say something, Katarina?
Of course.
It was sort of like during the day, we had always over 70 or 80 people on most sessions. Mm-hmm. And in the opening, I think I sort of the largest number was 125. So it was very good to have.
I noted down 131 at one point.
Oh, that's great. Yeah, even better.
So yeah, it's really good attendance. And really nice that we managed to pull this through in such a good way. We would like to, of course, thank our very interesting keynote speaker, Christian Tominski, for a very interesting talk, even though, and for his patience with all the delays this morning. And all the session chairs that we have had during the day for triggering a discussion and posing very nice questions. You have made this workshop really great. And we would also like to thank, of course, all the authors and presenters here today for great work and great discussions. A great thanks also goes out to the program committee that has helped us make this selection and has provided with very useful and comments and reviews during this process. And finally, the Eurographics and Eurovis team for making all of this possible, for helping us with all the technology around, and making it possible for us to have this workshop in this manner. Great thanks goes out to you too.
And this was a slide I put in to thank everyone, including you, Katarina.
And thank you, Chagatai and Michael. It has been really a pleasure for organizing this together with you, and thanks for all the input from our steering committee, Daniel and Jörn. And do you want to say some words about the future, Chagatai?
Yeah. Just a sort of a few final remarks. As you heard in the beginning, we are sort of we are in discussion with a few journals, and then you will get some emails from us about like invited extended papers. Last year we had a special issue at ACM, Transaction Interactive Intelligence Systems. This year we are moving into an invited paper mode to to different journals. There will be more updates on this on the EuroVA pages, and we will send emails directly to the authors. So we want to continue this tradition to have special issues and extended journal papers coming from EuroVA. So you will see more of that, and there will be more updates on that from us. And I mean, this is an update about EuroVA 2021. I know very little about this, so
well, I do know that it will be next year. EuroVis will be in Zurich, Switzerland. I am not entirely sure about the exact dates. I think it will be the second week of June, but I'm not saying that with extreme confidence. But hopefully next year we will be able to meet live in Zurich instead. Hopefully.
I mean, especially if Tatiana gets that system deployed on all hospitals. All right. I think with that, we would like to thanks everyone again. Keep the discussion going. The Discord channel is open, but I guess there'll be lots of channels where we can talk over EuroVis and over the week. The YouTube channels will also stay for a while. I don't know, Katarina, how long, but do you know? For at least
for this week. Then I think that there will be edited and the videos will be kept on for longer.
That's great. So let's keep talking and discussing and socialize as much as possible.
Exactly. So make sure that you join also the opening session of EuroVis that starts in about half an hour. That will be followed up by a virtual social event. So we can socialize more after that.
Okay. So enjoy your social events wherever you are, and take good care, and talk to you more. Bye everyone.
Thank you very much. Bye everyone.
Thank you.
Well done, great. I can imagine how difficult it